Hi everyone. I'm going to discuss sequence and series for today. So when we say sequence, it's a progression which is or with a list of numbers or objects in spatial order. Now we denote a sequence by a sub 1, a sub 2, a sub 3, and so on by the symbol a sub n and the kth member or term of the same sequence by a sub k. Now, the symbol a sub n is often called as the general term of the sequence. So, we define a sequence usually by an equation, and we make use of a sub n to describe the symbol, and we equate that on whatever equation or inequality we represent that sequence. Now, the elements in a sequence can be ordered pairs, sets of sets or other mathematical objects, but we will focus on sequences whose elements are real numbers, especially those follow a certain logical order. Now, by definition, a sequence is also a set. And this implies that sequences may either finite or infinite. So when we say finite, so we can count the number of terms in a set. So for example, if we like define a sequence by a sub n equal to like 1, 2, 3, 4, 5. This sequence is finite where n is less than or equal to 5 but greater than or equal to 1. Okay. So on the other hand, if like we define a sequence equal to n such that n is greater than or equal to 0, or the terms are positive integers, so we do not know how many exactly positive integers do we have, so we consider that sequence as infinite sequence. Now, some sequences cannot be easily defined by equations. So, for example, if the terms are 2, 3, 5, and 7. So if we're going to like describe this sequence using an equation, we cannot. Instead, we can just make use of statement that this sequence a sub n is the first four terms of prime numbers, or the first four prime numbers. Okay. So, but usually in our discussion, we're going to generate a pattern or define a sequence using an equation. Okay. And we I was able to define sequence as a set also. However, sequences and sets have two fundamental differences, and we have to discuss each difference. Like for sequence, the terms of a sequence are arranged in order. So for example, if we have a sub n equal to a finite sequence with terms 1, 2, 3, 4, 5, and this is different from a sub n with terms 5, 4, 3, 2, 1, because order matters as regards to sequence. So meaning that's why we have the notation a sub 1, a sub 2, a sub 3 for the first, the second, and the third term. Now, take note that in the first sequence here, the first term is 1, while here the first term is 5. But it's not the case in set where the elements are randomly arranged. So for example, a set defined by a sub n with elements 1, 2, 3, 4, 5 is equivalent with the set defined by or elements arranged in this form So as far as the two sets are concerned here, the two sets are equivalent. So going back with the definition of equivalent sets have the same cardinality or same number of elements. But most importantly, the two sets are equal sets. Unlike if we're going to consider the two sets sequence, so we cannot say that the two are equal sequence or same sequences. So they're different. But in the set, they are equal, they are the same because elements of a set can be randomly arranged. Okay. Now for sets, repeated elements of a random or repeated elements of a set may be eliminated without affecting the set itself. For example, if we have elements under set A sub n, negative 1, 1, negative 1, 1, negative 1. So we have another set defined by negative 1 and 1. The two are equal sets, though the two are not equivalent, but the two are equal sets because repeated elements of a set may be eliminated. But it's not the case with sequence because A sub n, for example, with terms, sorry, negative 1, 1, negative 1, 1, negative 1, and another sequence with terms negative 1, sorry for this. So we have so the two sequences here are different. Okay. So the two sequences here are two different sequences. So now the next thing that we're going to do is to generate a pattern from each sequence here that I'm going to present. So for number one, the first four terms are given. So we have 3, 5, 7, and 9 respectively. So for us to generate the pattern, we have to see the or describe consecutive terms like 3, 5. So in the definition of the sequence, the term is obtained by adding, usually we add a constant value or we multiply a constant factor to obtain the next term. But looking at the terms, the first four terms, for example, the first term is 3 and then the next term is 5. So what value have we added to obtain 5? Same goes with the third term 7. What value we have added from the previous term 5 to obtain 7? So if you notice, we are adding a constant value of 2. And that constant value of 2 will be part of the pattern. Like, for example, if we have a sub n equals 2n, and then we try to substitute n equal to 1 if we want to identify the first term. And the first term is 3. So if we substitute 1 to n here, so we only have 2, and that's different from 3. Now, what value are we going to add to 2n to satisfy the first term 3? So if 2 times 1 is 2, so we need to add 1 to obtain 3. And this is basically the pattern. So if we will try to check, like, is a sub 2 equal to 5 if we use this pattern? So we will substitute 2 to n since we are looking for a sub 2. So this is 2 times 2 plus 1. So this gives us 5, which is actually 5 here. And then we'll try again for a sub 3. So we will substitute 3 to n. So we have 2 times 3 plus 1. So this gives us 7. So really, this is the pattern, the general pattern for the first sequence. And then here, looking at each value, it seems like the next term was not obtained, or was not obtained as we add a constant value. And very obviously, we may concentrate on multiplying a constant factor. But it seems that as like we divide 8 by 2, for instance, we have 4, and 26 by 8, actually it will not come up with an exact value. So probably we can like come up with another sequence and compare that sequence with this original sequence. For example, if if we're going to like add um 1 to each, so we'll add 1 to 2, so we have 3, 8 to 1, we have 9, then 26 plus 1, we have 27, and then 81 for the fourth term. Now, we see a pattern. So each term here is actually power of 3. Okay? So we can like come up first with this one and then go back with this. So we have a sub n, for example, since I've mentioned that this is power of 3, maybe we're going to raise 3 to the n power. So if we have 3 to the n, like if we're going to verify if we substitute 1 to n, so that's 3 to the first, it matches with the first term here. Same goes with substituting 2 to n here, and that's 3 squared, so it matches with the second term here. But the problem here is this is not the given, instead this is the given. So what we're going to do, same with what we did in the first example, is to adjust, no? And to aim for the first term of the given sequence. Since this is 3, as we substitute 1 to n, so what value are we going to add to make this equal to 2? So if 3 to the first is 3, then we will just add negative 1, or we will less 1 from 3 to the n to obtain 2. And we have to check if that applies to the rest of the terms of the original sequence. Like if we're going to substitute, if we're going to solve for a sub 2 using this pattern, are we going to come up with 8 as our a sub 2? So if so, then we come up with the correct pattern. So if we have 3 and then our n is 2 minus 1, so this is 8. So which matches with 8 here. And we can try it with the third term. So we have 3, substitute 3 to n, and then minus 1. So this is 27. Okay, so this is 3 cube, 27 minus 1. So this becomes 26. So really, this is the pattern. Okay. Now, take note that the terms of this sequence are all one, but the sign is alternately placed. Like one is positive, the other one is negative, the next term would be positive, and so on. Now, if we're going to consider the alternation of the negative sign, so maybe we will be working on a negative factor. Like, for example, if we have positive 1 and we multiply that with a negative factor, so that will result to a negative value. And then multiplying that negative value to another negative factor, that will result to positive. So meaning the negative sign is alternately placed. So meaning we're going to multiply a negative factor. But everything there is 1. So maybe we'll consider negative 1 as the base. So for example, a sub 1 here. So maybe we'll raise negative 1 to the n power, and we'll try to do necessary adjustment for us to arrive with the general pattern. Like if we want to verify if this will match with all the terms here, like if we're going to substitute 1 to n and we are actually solving for the first term. So if we substitute 1 to n here, so negative 1 raised to the first power is negative 1, but this is 1 positive. So as what I mentioned about the alternately place of sign value, maybe we can multiply or we can add a negative factor on the pattern. So we write a negative 1 factor here. So as we solve for a sub 1, this will be negative of negative 1 to the first power. So -1 when raised to the first power is -1, but we multiply this with another negative factor, so this will result to 1. And for a sub 2, so this is negative of -1 raised to the second power. So we know that any negative expression when raised to the even power will result to positive. So this is positive times negative. So we have -1, which is actually the second term. And for a sub 3, so this is negative of -1 to the third. So any negative expression when raised to the odd power is negative times negative. So this will be +1. So we come up with this pattern. Also, if like we're going to consider, we have this -1 to the n, and we resulted with the second term instead of the first term, because this is equal to -1. When we substitute 1 to n, maybe we can move like we less 1 from the power of n. So we could have to the n minus 1 instead of to the n. So that when we like solve for a sub 1, so this is quantity -1 to the 1 minus 1. So this is -1 to the 0. So this gives us 1, which is actually the first term here. So same goes with a sub 2. This is quantity -1 to the second minus 1. So this is -1 to the first. And this gives us -1. So you will agree that a sub 3 will be equal to -1. So either of the two will be considered as the pattern for number 3. Now, a series is highly defined as or generalized as the sum of all the terms in a sequence. So as we add all the terms, we now introduce series. So however, there has to be a definite relationship between all the terms of the sequence. So we can like associate series to sigma notation. Okay? So so this is the left side here is actually series, and we transpose or transform this into sigma notation, like summation of a sub I from 1 to n. And then n here is referring to the number of terms, how many terms there are. So for example, we're going to write a notation for each. So it's necessary that we know how to uh, define each series by a general pattern, because a sub I here is the general pattern. So in number 1, like we have a sub n here. So let's generate a pattern first. We know that we are adding constantly a value of 10 from the previous term to obtain the next term. So we start with our pattern 10n, and then upon substituting 1 to n here, we come up with 10 times 1, which is 10, not the same with the first term 3. So we will add a value such that this will result to 3. So we have 10 here, so we just have to less 7. So we'll come up with 3 as the first term. And this is also, or this also applies to all the, or to the rest of the terms. So we now have the sigma notation represented by this series, summation of 10n minus 7 from 1 up to how many terms? 1, 2, 3, 4, 5, 6, up to the 6th term. So that's how we represent this series into notation. For this, very obviously that the terms were doubled, no? The previous term was doubled to obtain the next term. So we have a sub n here. So meaning we have a constant factor 2. So we will raise this to the n power. Now, as we substitute 1 to n here, this is 2 to the first, and this is 2. And this is not the first term, actually. So this is the second term. And also, as we substitute n equals 2, so this would be 2. This will be like, I mean, as we substitute rather n to 1, so we have 2 to the first 2. So 2 is the second term here, while we are trying to solve for the first term here. Likewise, if we are going to substitute n to 2, so that would be 2 squared 4, and we come up with 4. which is supposedly the second term here, but in the given in this given series, 4 is the third term. So it's advanced with one term. So what we're going to do is to less 1 from n. So as we substitute 1 to n here, this will now 1 minus 1, 0, and 2 to the 0 is 1. So really, we are trying to solve for the first term, and we come up with really with the value of the first term. So this must be the pattern. Actually, whenever we multiply a factor, we always associate this with placing the first term as part of the pattern. But since the first term is 1, so no need for us to write 1 times this, since the result will be 2 to the n minus 1. So this will be the pattern. Now, we can now generate a sigma notation for this series. So we have summation of 2 to the n minus 1 from 1 to infinity. So since there are infinite terms here, so we will just write n. But as I introduce infinite terms in the next discussion, so this may be replaced by n equals infinity. Okay, so for now, it will be like that. So here, obviously, we're adding 8 from the previous term to obtain the next term. So we have a sub n equals 8n. But as we substitute 1 to n here, so we have 8 times 1, so 8. So we just have to less 1 to this to make this fit with the first term 7. So we have 8n minus 1. So we can now transform this into sigma notation. So this would be summation of 8n minus 1 from 1 to 1, 2, 3, 4, 5, 6. N equals 6. Okay? Now, infinite series, so we can evaluate series. So for example, if we cannot evaluate the sum of a series, then we can consider that as divergent if we cannot evaluate. But if we can evaluate the sum, so we consider that as convergent. Okay, so let's try to work on the missing terms and try to generate a pattern for each. Now here, obviously, the sequence is decreasing, like it decreases by 10 units. So most probably this is 15 and this is 5. So since this decreases by 10 units, so we represent that by negative 10n. And then we have to think of a value when added, like if we substitute n equals 1, so we have negative 10 times 1, we have negative 10. And then what value are we going to add to obtain 35? So we have to add 45. So this is the pattern. So 45 minus 10 is 35. Now here, if we're going to consider the first two terms, 2, and then we have 2 square root of 2. So when we say 2 square root of 2, so that's 2 times square root of 2. So basically, we like multiply the first term 2 by square root of 2 to arrive with 2 square root of 2. Now, the next term is 4. So we can assume that 4 is actually the result of multiplying 2 square root of 2 by 2 square root of 2. So that is we have for us to find out. Okay. So is the third term 4 derived from multiplying 2 square root of 2 by square root of 2. So going back to multiplication of radicals, so we can multiply radicals as long as they have the same index and we just multiply the radicand. So this is equal to 2 times square root of 4. And we know that 2 times square root of 4 is 2 times 2, and it's 4. So really, we multiplied square root of 2 to previous term to obtain the next term. So most likely, this would be 4 times square root of 2. And 4 times square root of 2, 4 square root of 2 times square root of 2 is 8. And then 8 times square root of 2 will be 8 square root of 2. So the general pattern will be, will begin with square root of 2. And we raise this to the n. Since if you remember in the previous slide, we will always associate the first term as the factor of this pattern. So we can place like 2 here. And if we want to verify if this pattern satisfies the terms, the listed terms, like is a sub 1 would be equal to, when we substitute n to 1 here, will be the same with 2. So if this is 1, so square root of 2 to the first is square root of 2, and multiply this by 2. So this will be 2 square root of 2, which is the second term, but we are trying to solve for the first term. So instead, we will just less 1 from the power, and that would match with the first term already. So if this is 1, so this is square root of 2 to the 0. We know that square root of 2 to the 0 is 1 times 2, so that's 2. So this will be the pattern. Now for number 3, it decreases, but we are not decreasing, subtracting a constant value. So maybe we can consider a constant factor. So by inspection, if you look at 729 and 243, if you, since that's decreasing, we will consider division instead of multiplication. Like, if we divide 729 by 243, what's the value? As well as if we divide 243 by 81, what's the value? And you will come up with the same value, which is equal to 3. Meaning we are just dividing the previous term by 3 to obtain the next term. And that's exactly the same with multiplying 1/3 from the previous term to obtain the next term. So we will multiply 81 by 1/3, or we will simply divide 81 by 3. So this is 27 divided by 3, 9 divided by 3, 3. Now, the pattern would be, since we want a factor, we want multiplication here, so we're going to use 1/3. So we're going to raise 1/3 to the n. And again, we're going to make use of the first term here as part of the pattern. And we will try to see, substitute n to 1 here. And as we evaluate this has to be the first term. And 1/3 to the first is 1/3. And 1/3 times 729 is not 729, definitely. It has to be 243. So it has to be adjusted. So the exponent must be n minus 1 instead. There. Now here, it's increasing by 5. So if we're going to add 5 to negative 15, this will be negative 10 plus 5, negative 5 plus 5, 0. So we're going to consider the constant value of 5, so 5n. If we substitute 1 to n, so it's 5, but it's negative 25 here. So if we're going to like, what value are we going to add to 5n to obtain negative 25? So it's 5. If this is minus 30, like this is 5 minus 30, so this will result to negative 25. And lastly, this is very predictable sequence. Like we were going to add 11, so plus 33 is 44. So here plus 11 is 66. Now a sub n here, so we'll start with 11n. Since this matches already with the first term, so no more constant value to be added, and that's a sub n equals 11n will be the pattern. So to wrap up, so I've just introduced you to the general definition of a sequence and series. And the most important thing is, how do we generate a pattern from a sequence? And another thing is, it's necessary that you know how to generate a pattern for a sequence, since we can make use of that also as we transform a series into sigma notation. So in the next discussion, I will be introducing you to the different types of sequence. So bye for now.